Welcome to this explainer. Today we are completely decoding the absolute fundamental rules that govern exactly how everything in our universe moves. Look, whether you're actively studying for your Cambridge 0625 syllabus, trying to boost your grade boundary, or honestly just curious about the invisible mechanics of the world around you, we're going to break down the core concepts of physics from the ground up. We're talking forces, mass, weight, and motion, and we're going to make sure you truly understand them so you don't fall into the common traps that cost people easy marks. Let's get right into it.
Okay, so here's our roadmap for today's session. First, demystifying everyday forces. Second, we'll tackle mass versus weight. Third, we dive into the mystery of freefall. Fourth, calculating resultant forces. And finally, number 5, an introduction to momentum.
Let's start right at the beginning. Section 1, demystifying everyday forces.
At its absolute simplest, a force is just a push or a pull exerted by one object onto another. You push a door, you pull a chair. But, in physics, we have to be way more precise than that. A force isn't just an amount of effort. It has a very specific direction. And this is crucial, especially if you're answering exam questions, because a force has both a size, which we call magnitude, and a direction. It is officially classified as a vector. If you just give the size and forget the direction, you're missing half the story. And the standard unit we use to measure this vector, that's the Newton, represented by a capital N.
Now, hearing the word Newton might sound a little bit abstract if you're just starting out, so let's ground it in reality. I want you to have a feel for what this actually means. To give you a practical sense of this unit, 10 newtons is exactly the amount of typical force required to simply switch on a standard bathroom light. It's just a small, everyday push, nothing crazy.
Before we continue, I want to quickly remind you to subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, back to the physics. Look at how these invisible vectors are acting around us constantly. It's like a giant tug of war happening everywhere. Notice the upthrust from the water keeping a heavy boat afloat. That's directly battling the downward pull of the boat's weight. We see tension in a rope being pulled. We see friction resisting a sliding box. And check out the massive forward thrust of an aircraft engine. That engine is literally cutting through the opposing force of air resistance. Literally, every single interaction around you involves these pushes and pulls.
Moving right along. Section 2, mass versus weight.
Listen closely because this right here is literally the #1 place I see people get confused. Mass and weight are not the same thing. Mass is simply the amount of matter in an object. It's measured in kilograms, and it absolutely does not change based on where you are. You are made of a certain amount of stuff. Weight, on the other hand, is a force. It is the actual gravitational pull acting on that mass, and because it's a force, it's measured in newtons. It's crazy to think about, but even the bathroom scales we use daily are marked in kilograms, right? But they are actually detecting your weight. The scale is quietly calculating your mass multiplied by the local gravitational field strength, which we call G, and then converting it back to kilograms for you.
Stop scrolling for a second, because watching this concept play out across the solar system is just fascinating. Notice how our astronauts' mass stays perfectly locked at 100 kilograms, no matter where they travel. That's the amount of matter they are made of. It's constant. But look at their weight. It wildly swings from a heavy 1,000 newtons right here on Earth down to just 160 newtons on the Moon where gravity is way weaker. And then, absolutely zero when they're floating out in deep space. Zero weight, but they still have exactly 100 kilograms of mass. Mass is your anchor. Weight depends entirely on your location.
All right, Section 3, the mystery of freefall. Let's see what happens when gravity is running the show by itself.
You might instinctively think heavy things fall faster than light things. And honestly, in our everyday experience with air around us, they usually do. But if we take a specialized tube and pump all the air completely out of it to create a vacuum, removing air resistance entirely, something magical happens. Gravity accelerates a super delicate feather and a really dense heavy lead ball downwards at the exact same rate. They hit the bottom at the exact same time. Without the air pushing back, gravity treats all masses totally equally when it comes to acceleration.
And that uniform acceleration for objects in freefall is universally denoted by the lowercase letter g. Now, near the Earth's surface, this acceleration is approximately 10 meters per second squared. What does that actually mean in plain English? It means that for every single second an object is falling in a vacuum, its downward velocity increases by 10 meters per second. So, after 1 second, it's falling at 10 meters per second. After 2 seconds, it's at 20, and so on. It gets faster and faster at a perfectly steady rate. Hey, quick pause. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. We've helped thousands of students improve their understanding. Join them right now by subscribing.
Okay, let's put this into practice. Section 4. Calculating resultant forces.
Let's look at this 200-kilogram rocket. It is a textbook perfect example of opposing forces in action. It has a powerful engine, providing 3,000 newtons of upward thrust. Awesome. But it's also constantly battling against the downward pull of its own weight due to gravity. To know what the rocket is actually going to do, is it going up, is it falling down, we need to calculate what we call the resultant force. That's the net total of these competing forces. It's basically figuring out who wins the tug-of-war.
Let's break the math down step by step. First, we have to calculate the rocket's weight. We do this by multiplying its mass of 200 kilograms by Earth's gravitational field strength, which we know is 10 newtons per kilogram. That gives us exactly 2,000 newtons pulling downwards. Second step, we identify our upward force, which is the 3,000 newtons of thrust from the engine. Finally, we calculate the resultant by subtracting the downward pull from the upward push. 3,000 minus 2,000 leaves us with a resultant force of 1,000 newtons. And the direction? It's pushing upwards because the upward thrust was stronger. Because that resultant force is upwards, the rocket successfully accelerates up into the sky.
We're in the home stretch now. Section 5. Introduction to momentum. Once an object is actually moving, we have to talk about momentum. The core equation to remember here is quite elegant in its simplicity. An object's momentum is simply its mass multiplied by its velocity. I like to think of it as a measure of how much oomph a moving object has. How hard is it to stop? If you increase the mass, or if you increase the speed, the velocity, the momentum scales up proportionally.
Take a look at a massive vehicle like this cargo truck. It possesses a massive amount of momentum. It has a very, very large mass, and when it's cruising at highway velocities, those two numbers multiply into something huge. Because of that immense momentum, it requires a correspondingly massive resultant force, specifically friction from very powerful brakes, to finally bring it to a safe stop. You can't just stop it instantly. The forces involved have to perfectly counter that massive momentum.
We've covered a ton of ground today, all the way from the single newton required to flick a light switch, up to the massive resultant forces holding rockets and trucks in check. But I really want to leave you with this final, thought-provoking question to test your new understanding. If a steady velocity, even a velocity of absolutely zero, means that all the forces acting on an object are perfectly balanced, what unseen forces are acting on you right now just to keep you sitting still in your chair? Think about it. Gravity is constantly pulling you down, right? So the chair must be pushing up against you with the exact same amount of force. Physics isn't just theory on a page, it is actively holding you in place at this very second. Before you go, here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Drop a comment below with your biggest physics challenge and keep questioning the invisible forces around you. See you next time.